Okay, good morning, everyone. I take it the microphone is on. It seems to be. So before we get started today, a couple announcements. First of all, remember that the choice of technology for your term paper is due at 8:30 Wednesday morning. This is not a long and complicated assignment. It's probably about 3 to 4 sentences tops. It's essentially free points, so I would strongly recommend you get it in by 8:30 on Wednesday. Question? Yeah, so submit it on Blackboard. So there's the submission portal. If you go to like the assignments page and then in the term paper folder, it's officially a test as far as Blackboard is concerned. It's not really a test. That's just how I have to classify it to get the input and response stuff working right. But do make sure you get it submitted before the deadline, 8:30 on Wednesday. Also then, remember Wednesday, we have our first quiz at the end of class. So that'll be covering the GPS unit that we finished last week and the homework that was due 7 minutes ago. Solutions to the homework assignment have now been posted on Blackboard. Take a look at them, come to office hours with questions, post questions on Blackboard. There are already a couple questions on the discussion forum about the format of the quiz and whatnot. So read those over. In particular, there's one regarding what types of calculators are allowed. Just as a general note on the quiz, they're designed to take, I'll give you 15 minutes. In my experience in past semesters, most people are done in 5 to 7. So we'll start somewhere 9:30, 9:35, just depending on where a good break is in the lecture. And we'll do the quiz there at the end of class on Wednesday. There will be 3 questions. That'll be pretty much true of all the quizzes this semester. The very last one might be a little bit different, but we'll talk about that in December. What I would recommend for studying is look over the homework, look over the solutions, and a lot of times, there might be a question about some of the math concepts. There might be a question about the technology itself. And most importantly, in a lot of cases, and sometimes the homework problems are designed to do this as well, the questions might be geared more towards why did we do something? Remember, one of the big components of this class is thinking about critical analysis and how do we approach problem solving. And so maybe we're going to ask, why did we do something? More than asking maybe, what is that concept? Okay? And so to try to figure out what's the rational approach and why did we talk about this concept or this idea in class and what was its relevance to the technology or to the math concepts. Anybody have any questions about the quiz in particular that you'd like me to address here? Yep.
Did you just say what format the quiz would be?
So it's going to be short answer, maybe a small calculation, but 3 questions. And also everyone saw there's the sheet of possibly useful information on Blackboard. Should maybe pull that up here. If you come over into the Documents tab and go into the GPS folder, you'll notice there's this sheet of possibly useful information. This will be given to you on the quiz, so don't feel like you need to memorize that or do anything else. Just make sure you look at it, but this will be given to you on Wednesday. Okay, other questions? Okay, so then yep. So can I tell you what the location was for number 5? I have no idea what the location was, but the answer for part B was point 2. Would somebody like to ask maybe a more general question about question 5? Or is everyone just content looking at the solutions and we'll take it from there? Really? No one?
Why was it point 2?
Okay, why was it point 2? Well, why wouldn't it be point 1? Okay, my guess is a lot of people probably overthought this problem. So question 5 comes in, and it gives you this table. So here's the solutions. Like I said, you can look these up as well for all of the problems. It gives you this table of these different satellite positions and distances. What is that table telling you, in essence? So it's telling you the Cartesian coordinates of all of the satellites, and it's telling you your distance from those satellites. So when we come to part A, determine if each of the following points could be your location. What do we actually have to do? We need to check and see. So if, suppose we're at point 1. If point 1 is our location, how far does it have to be from the first satellite? Approximately 8,800 miles, because that's what we've learned from that piece of information in the table. So that's for satellite 1. How far must we be from satellite 2? About 12,500 miles. because that's the information that we were given here in the table, and a little bit, and we're just a hair closer to satellite 3. So for part A, what this is asking you to do is just verify what's the distance between point 1 and those 3 satellites. Did they all match the table? If they do, can that be our location, potentially? Yeah, because we're the right distance from all the satellites. If any one of the distances is wrong, can that be our location? No, because we're the wrong distance from one of the satellites. So in this case, it turns out for both points 1 and 2, both of them could potentially be our location if you go through and check those distances. Okay? So now, moving on to part B, what it then says is, if you also know that you're on the surface of the Earth, can you narrow down your location? So what does it mean to be on the surface of the Earth? It means we're about 4,000 miles from where? The center of the Earth. And so what we need to now do is verify between those 2 points, points 1 and 2, which one of them, possibly neither, possibly both, is 4,000 miles from the center of the Earth. And again, we can just use the distance formula. It turns out to actually be using sort of just spherical coordinates. You can just say r is equal to square root of x squared plus y squared plus z squared. And we see that point 1 is about 16,500 miles from the center of the Earth. So can that be our location if we know we're on the surface? No. And we see that point 2 is approximately 4,000 miles from the center of the Earth. So which point must you be at based on this information? Point 2. Yep. So you said you could be at point 1 and then went, so point 1 is probably not right because you're floating somewhere way off in space. And then you can find the latitude and longitude. That's certainly something you can do, but it's not necessary to solve the problem. Yep.
Yeah, I understand it now. But when I was doing it, I thought that the x point, I could try to plug into like this formula, like so like x minus x1. So like I use those x's and I try to plug into there to see which one came out to be closer to each other.
Okay.
And then you'll see that, but like so that's how I got point 1, and I see that now I'm completely wrong.
Okay, we'll work through it. This is, so I will say this up front. This is probably the hardest problem we're going to see all semester. Okay? So I told you at the beginning, the GPS was the hardest unit in my past experience. The good news is we're now done with it. Well, up to a quiz on Wednesday. And when I say this is the hardest problem we're going to see all semester, how many of you were able to finish this problem in less than 15 minutes? Okay, there are a handful of hands going up. How many did it in less than 10? Okay, keep up my hands. Given that, do you think that something like this is going to appear on the quiz? No. Okay. The quiz is completely intended that you should have no trouble finishing it in 15 minutes if you've been doing the homework, you've been coming to lecture, and you've been reading through the notes and keeping on top of things. Okay?
So you said we get points for like if you show how it worked and how we got there.
Yeah, so one of the big things in this problem, and this is going to be an ongoing theme throughout this course, is anytime there's sort of problems, so you notice a lot of those problems had sort of like the 1 or 2 star in front of them and then the points were a little bit harder. I try to give you some sense of difficulty of which problems I think are sort of the easier ones or the harder ones. This realistically should probably be a 3 star. But the idea there is, you know, even if you don't know how to solve it, if you see those 2 stars, that means I'm wanting to push you a little bit. And you've got all the tools you need to solve it. We've discussed everything, but I want to see just how far you can take the concepts that we've discussed. If you're stumped, certainly, you know, bring questions to class, bring questions to office hours, post questions on Blackboard. Probably the night at 10 o'clock the night before is not the best time to do it, but we're happy to answer them. But more than that, if you get stumped and you're looking at this and you still don't know how to solve it, then write a few sentences. What are you thinking? What are you trying to do? What approach are you taking? That's just as valuable to us when we go to grade because that helps us gauge what are you thinking. Remember, that critical analysis, problem-solving techniques, that's the main takeaway from this course, and that's really valuable information. Something that probably isn't going to get full credit, but in a lot of cases, especially on the harder problems, it can still probably get quite a bit on the homework. I mean, remember, 50% for just a good faith effort, the other 50% for actually getting the right answer. Just explaining what you're thinking in a lot of times can get you quite a bit. Okay? Does that make sense? Does that seem fair? Okay. Any other questions then about homework 1? Okay. Then if not, please review the solutions on your own time. Please, like I said, post questions. Either bring them to office hours, post them to Blackboard. In principle, you can bring them at the beginning of class on Wednesday, and we'll discuss them, you know, an hour before the quiz. Otherwise, I will leave that to you, and we'll move on with the course. Okay, so then, let's come back over. And so what we're going to do now is shift gears entirely. We're done with GPS. The letters GPS might appear in that order when we get to one of the later units, but for the time being, other than the quiz on Wednesday, we're done with that. And so we're going to shift gears entirely and do something a little different. And so looking back, if you remember on the first day of class 3 weeks ago, I gave you a survey and asked sort of what technologies did you want to see? It probably won't surprise anyone that either computers, phones, tablets, something of this ilk was the most commonly requested technology. Lots of you are very interested in these. We're going to lump all of them together, whether it's a computer, phone, tablet, to some extent a smartwatch, any other pieces of technology someone might want to sort of classify as a digital device that you can think of? An iPad, sure, tablet or an iPod. The music player, yes, very similar. Video games we're going to see video games as this unit progresses, but they're not really going to be the main focus. Okay? Because video games are more sort of, they use digital devices, they're not necessarily the digital device themselves. I'm sorry? So does that mean you could potentially do video games as your term paper? It's been done in the past. That being said, please do not all submit video games. If someone's looking for interesting technologies, there are always some really fun choices. I actually came up with an interesting one yesterday that I'm thinking about turning into a one lecture aside later in the term. But we'll come back to that later. Something that isn't even remotely digital. Other ideas, okay? So what are some uses for digital devices? You've got your computer, you've got your laptop, you've got your tablet. As we're going to see as today goes on and as this unit builds, these things all share a lot of commonality, which is why we're going to lump them into sort of one big unit. And when I say one big unit, partly we're going to say there's this one where we're combining them all together, but we're going to actually have units 2, 3, and 4 all deal with different aspects of digital devices. We're going to start this unit with what I call data storage unit and talk about how they work and how they store data. And then we'll talk about a little bit more of how they do the data processing in certain ways in later units. But we're going to be spending probably about the next month to 5 weeks talking about computers, tablets, phones in some regard. Anyway, so what are some uses for digital devices? How do you use your computer or your phone, your laptop, your tablet? Okay, we use it to communicate with other people. That's a great answer. And we're going to talk about that more in sort of the next unit. How do we actually transmit and transfer data from one device to another? What else do you use your computers for? Okay, to access the internet and get information. That's another great answer. But do you use it to procrastinate? Okay, there's a few people willing to be honest. What else do you use your computers for? Is that it so far?
Time management.
Okay, so time management. So you've got a calendar built in and help you manage your time better. Sure. Yep. Okay, yes. Yep, communication. We can send emails. We can do all sorts of things. Entertainment. What types of entertainment do you do on your computer or your phone or your tablet? Netflix. Okay, that's a generonym. We could also have Hulu or YouTube or things like that. Okay, we can play games. We've already mentioned video games a little while ago, but we can have other forms of entertainment in that way. You can listen to music on computers. So the idea here, there are all sorts of operations. So I listed here a couple. We've got word processing. Anybody do word processing on their computer? Like, does anybody use Microsoft Word? Okay, you've done word processing. You can do calculating and number crunching. Certainly communicating was mentioned. How about just storing or processing data? What about a database? Are computers useful for collecting and processing information? Yeah. That was, in fact, one of the big reasons they were developed some time ago. And the list goes on and on. And so take a moment now and sort of think to yourself, how many routine tasks in your day-to-day life either do not or potentially cannot use digital devices? Can you think of any briefly? Running, yeah, running. Well, I don't know if you're using a treadmill and it's got the really advanced, like the screen to keep you occupied, because I hate treadmills. Maybe they're digital devices. Do you use your iPod or your phone to listen to music when you go running? Neither do I, but a lot of people do, and so you're still using the digital device when you run. Yep. Sleeping, okay. In general, I mean, yeah, there can always be white noise machines, or does anybody like to fall asleep with their television on? Okay, so that can still sometimes be a digital device, but yeah, in general. Reading. What about a Nook? I'm just being obstinate at this point. Yes, these are all great examples of things you can do without technology, but you can also easily see how the digital devices are able to be used there as well. Okay? So anyway, the point here is, these digital devices have a huge range of application. And so, sort of starting off again, historically, what were the first computers? So think of computer now not as necessarily a digital device, but if you go back to like a 19th century dictionary and look up computer, it's going to tell you something like a person who computes things. Okay? So what historically speaking, was the first computer that humankind used? I'm sorry? I still didn't...
I just read an article about ENIAC. It was supposed to decode messages that were sent back and forth during World War II.
Okay, so maybe some sort of cryptography machine to encode messages that was used during World War II. I think computing goes back quite a bit earlier than that. Okay, a calculator. What kind of calculator? A human calculator. Okay, that could certainly be true. And what was the device that a lot of humans used to do their calculating? What was it? Are you thinking of an abacus? Yeah, there are things we used before abaci. Okay, so another term for a computer, these devices, is a digital device. Why is it called a digital device? Because it uses digits. What's the original form of digits from a human perspective? Fingers. Is this a digital device? Can you do, yeah, it is. There's digits. I got 10 digits. Some people have 8. Some people have 12. Most people have 10. Okay? Can you do computation on these? Does anybody remember from like elementary school looking at the powers of, or at the multiples of 9, where you could have, here's 9 and then 18 and 27 and 36 and 45 and so on and so forth by just moving your one finger about? Is that a way of doing calculation? Yeah. You've seen also the trick of there's you can add 1 plus 1 and get 2. Is that also a very naive way of doing computing? Sure. But was that a computation using digits? Yeah. So going back historically, hands, from a human perspective, were the original digital device. Certainly, more and more complicated things have been developed as technology progressed. One that we've already mentioned were abaci. Anybody ever use an abacus? Okay, a couple hands have gone up. Is it easy to do like addition and subtraction on an abacus? Yeah, how about multiplication and division? Not so much. This was actually historically one of the reasons why Roman numerals fell out of favor. Has anybody everybody's worked with Roman numerals, the L's and C's and M's and I's and V's and X's and all of that? Have you ever tried to add two numbers in Roman numerals? Think about adding the numbers 4 and 24. Where we've got now, what is it going to be, IV and XXIV, which naturally we all know the answer of 4 plus 24 is 28. Try to work that out using Roman numerals. Try multiplying 4 and 24 in Roman numerals. Arabic numerals are so much better, which is why they've been widely adopted, and everything but writing years at the end of movies. I don't know. But so as human civilization has progressed, we've found better and better and better ways to do computation, both with devices and in terms of how we think about numbers. More recently, going back into the early to mid 20th century, there was this idea of a vacuum tube. Okay, has anybody ever played with a vacuum tube? So it's a tube, and inside the tube is a vacuum. And basically, you can form really simple transistors out of these. And with these transistors, you can start to build electronic computers. Okay? Building up towards something like your phone. Now, These vacuum tubes were not necessarily particularly small. Back in the 40s, when they first started developing them, they might be like the size of what now is a 2-liter pop bottle. Sorry, I'm from the Midwest. 2-liter soda bottle. Okay? And so think about now, how many of those do you think, to build a computer? If each one of those can maybe do a very simple operation, is 1 or 2 vacuum tubes going to be enough? No, you're going to need maybe tens, if not hundreds, if not thousands, if not more. And so when they started actually putting together what we would call a modern day computer, electronic computer, how big were they? They were the size of rooms, something probably not that unlike this lecture hall. And we'll talk about compute power more momentarily, but how powerful do you think those computers were? Probably not very. Does your smartwatch have more computing power than that computer did? By orders of magnitude. I mean, the answer is not just yes, the answer is expletive deleted yes. Okay? And so if you're curious about sort of the development of computers for some historical context, I've got some links here in the slides that you should check out. But, I mean, remember, this is sort of very much a modern invention in terms of being able to produce this many computations and to have this much computing power. It took us millennia to go from hands to abaci. It took us another 100 years, or several hundred years, to go from abaci to vacuum tubes. And in the last 70 years, the progress we've made from a really, by today's standards, a really bad computer filling this entire room to realistically a very good computer fitting in this phone in the matter of about 70 years. I think that's really kind of impressive as a civilization. Okay, so modern computers don't really use any of those previous technologies to actually do the computing. They don't use hands. Okay, yes, you have to type on your keyboard, and maybe you still got a mouse or a touchpad to interact with the computer, but the computer's not actually using hands. There's not some really tiny person counting things on his fingers or her fingers inside your computer. Okay? They don't use abaci. Again, they're too big and they're too slow. They don't use vacuum tubes anymore. Again, they're too big and they're too slow. The technology that we're now using, which was largely developed in the 70s and the 80s, is what's called integrated circuits. Anybody heard of those before? A little bit? Okay. We're not going to go into a whole lot of details. The key point here is they allow fabrication of really, really, really small things. So we mentioned on the last slide that these vacuum tubes could be used to build transistors. Transistors are basically the fundamental electronic unit in a circuit that enables our present computation to occur. I don't really want to go into much more detail than that, but just think of it as sort of a fundamental piece of computing. Integrated circuits allow transistors to be built at the micrometer scale when this technology first started, sub-micrometer scale, and most of the computers that are now being built, so if you were to go to like IBM or Intel or AMD and ask them basically how big are their transistors, anybody want to take a guess sort of what the dimensions, what the length scale is of those transistors? Do you think it's less than kilometers? Yeah, what do you think? Okay, so it's maybe on the order of micrometers? Okay, micro even down to a nanometer. So everybody remember micro is the prefix for 10 to the minus 6? So like 1,000th of a 1,000th. What's the next metric prefix down? Anybody remember 10 to the minus 9? It's not femto, that's 10 to the minus 12. It's nano. So a nanometer would be a billionth of a meter. The anecdote I've always heard is a nanometer is basically the length human hair grows in about a second. I don't know if that's entirely accurate, but that's what I've heard. Okay? So it's not a very big distance. Okay? So where do we think? So you said sort of nanometers to micrometers. Do you want to maybe narrow that down a little bit more? Okay. So it's about tens of nanometers. Most modern transistors are somewhere in like the 20 to 40 nanometer range. Okay? So think about now, has anybody ever pulled their computer apart or you've seen a computer chip? Like, about how big is it? Maybe, a couple square inches, maybe 2 or 3 square inches? How many transistors, if each one of those is taking up 30 nanometers, how many of them can you shove on that chip? You can put a lot of them on there. Okay? That is the primary advance that's enabled computers today to become as powerful as theirs. The fact that we can just shove so many transistors on that chip because we've gotten really good at fabricating really small things. And so if you actually look and try to then figure out how have computers gotten better over time, there's this graph here, and I apologize that the font is really, really hard to see. It's very small on the slide. But basically what they're showing here on the x-axis, or on the horizontal axis, is the date of the computer, and I apologize that it also only goes up to 2011. And you can now start to see how many transistors were in that computer. And notice when they started this chart back in 1971, the number of transistors was about 2,300. Okay? Versus, we can now plot, and as we go through the years, you can start to see all of these dots represent new computers that were fabricated and when they came online. Going up to, you can start to see some AMD, there's some Itanium. Anybody remember the old Pentiums from maybe the 90s and early 2000s from Intel? Anyway, you can see those are sort of here in this range. We get up in the 2000s, and now notice how many transistors are we now putting on a particular computer. It's about 2.5 billion or so. That is what, a 6 order of magnitude increase in roughly 40 years? And what happens is this ends up basically meaning there's this exponential increase. And this is more or less known as Moore's Law, after an engineer at IBM named Gordon Moore. And basically the idea here is he postulated back in the 70s that the number of transistors on a machine would double about every 18 months. And believe it or not, we've maintained that pace for 40 years. Hey, you got a question?
That's probably increased since 2011, right?
It has probably increased since 2011, but not as much as you might hope. So one of the issues when we're starting to think about computing now as we move forward is we've relied a lot on this increase that said, well, you know, if we've got this really big computational task and we want to do something, but our computer's not quite good enough to do it, well, let's just wait a year or wait 2 years and the technology will get to the point that we can. We're running into fundamental limitations right now on being able to push this. We can't really make the transistors any smaller. We get to sort of that 20 nanometer mark and something weird happens. Anybody want to take a guess what that is? So yes, let me recap your answer on the microphone, but yes, essentially. Basically, if we make the transistors much smaller than about that 20 nanometer range, quantum mechanical effects start to enter and degrade the device performance to the point that we can't actually control or guarantee that the transistors are going to work the way that we intend. And this is putting up now a very fundamental barrier on keeping Moore's Law growing because we just can't actually shrink the transistors anymore. So does anybody also remember, if you've looked at computers a lot, does anybody know how many cores your laptop has? Anybody know what I mean when I say core? Okay. So throughout most of this history on this chart here, each computer had one core, which is to say there was basically one chip in the computer that was handling all of the information and doing all of the data processing. In about 2000 or to 2005, a lot of the chip developers started realizing they were reaching the limit of the integrated circuitry technology, which said we can keep making these transistors smaller. And they said we need to find new ways to be able to increase the transistor count without actually reducing the number of transistors, because we're just not going to be able to make them that much smaller for much longer. And so what they started doing when they started building commodity computers was saying, let's put multiple cores in a computer. So instead of having just one processor, if you have like a 2-core machine, you actually have 2 independent processors running in your machine, which in effect doubles the number of transistors. Take one chip, put in 2 chips, and you've doubled. Modern day, most computers, at least commodity computers, if you were to go to like Apple or Dell or someplace like this and just buy a computer, you're going to get probably 4 cores. That's what's usually available right now. On more business end machines, commercial end or experimental computing, having cores up 512, 1024 is not uncommon. We're going to talk about momentarily some computers that might have more than 1 million cores that are out there. And so what I'll say then, sort of the idea of computing is, how many of you think adding more cores is going to make all of our problems go away? Okay, I see a lot of people shaking their head no. What's the issue? If we were to say, let's put 2 cores on the machine, does that mean we're going to solve all of our problems twice as quickly? Why not? Well, so each core still has its own limit. That's true. But more importantly, okay, let's ask a different and related question. How many of you have a cat at home? How many of you have a friend that has a cat at home? Okay, 10 of you are paying attention. How many of you have more than 1 cat? A couple hands go up. How easy is it to get your 2 or 3 or 4 cats to do simultaneously what you want all of them to do? It's not possible. Computer cores are a lot like cats. And they're sometimes hard to control. And the issue is when you start putting all of these different cores into the machine, you have to get them to cooperate with each other. Okay? It's not enough to just say, you go do your thing, and you go do your thing, and you go do your thing. They have to communicate and coordinate their effort to get meaningful work done. And it turns out that is extremely complicated. So now scale that up, and I mentioned a moment ago that there are machines that have 1 million cores. Think about trying to get your 1 million cats to cooperate. Who thinks that sounds like fun? Who thinks that sounds futile? Yeah, there you go. The good news is it's both fun and not futile. Okay, so one of the big things then to think about when we start talking about computing is we've mentioned and sort of hinted at this idea of computing power. What do we mean by compute power? If I were to ask you, how good is your computer? How would you answer that question? Would you say your computer is just really good because you just bought it? Maybe not. Okay, so maybe how fast is your computer? Okay, and so we could have a metric that way. We could say, well, this computer is X fast and this computer is Y fast, and we can compare the two to say which is the better computer. Okay, that's certainly one reasonable approach. What else might we want to look at when we're determining how good or how bad our computer is? Anybody have any ideas? Okay. Well, there are plenty. So we mentioned speed already. Yeah. How much information it can hold? So maybe how big your hard drive is. Okay, so a bigger hard drive can store more stuff, which might give you a better computer. Whether or not it makes errors. Let's assume for the purpose of this discussion the computers don't do that. Yes, that is certainly something in the real world we have to worry about, but we're not going to touch that here. Yeah. Okay, the RAM. How much memory does the computer have? And we'll discuss the difference between memory and hard disk. It might be later today. It might be on Wednesday. But we'll come back to that point. Okay, so the idea is there are lots of metrics that we can use to measure computing power. The one that's commonly used in practice is this idea of what's called a flop rate. And notice that the flop is all in caps because it's an acronym. And what it stands for is a floating point operation. So think of flop as floating FL, floating point operation. And what do you think we mean by floating point operation? So it'd be any sort of arithmetic operation involving two numbers. So if I were to ask you to add 3.141593 and 2.718282, that is one floating point operation. So when we think about flop rate and a way to measure compute power, what we're really talking about, perhaps, is what's the flop rate of the computer? How many floating point operations can a computer do per unit time? If a computer can do more floating point operations in the same amount of time, is that arguably a better computer? Yeah. So to think about flop rate, go back maybe when you were in elementary school and learning about arithmetic. Did anybody ever have to do these mad minutes or math minutes where your teacher would hand out a sheet and there's like 50 addition problems on it? Okay, so maybe there's the first row. And you can see, so 8 plus 11 is, of course, 19, and 9 plus 10 is 19, and 1 plus 8 is 9, and so on and so forth. Okay, how many of you, if you were given a sheet of those 50 arithmetic problems, how many of you would get it done in a minute? Okay, some hands go up. How many of you would get it done correctly in a minute? Okay, more hands go up. Interesting. So coming back to your point of, yes, accuracy is important. But are you going to get it done in much less than a minute, or is it going to take you most of that minute? It's going to take you most of that minute. So from a human perspective, our flop rate may be around, I don't know, 60 floating point operations per second. Does that seem particularly high? From your experience, can a computer do it faster? Yeah. So the question now is then, how do we look at the flop rate? Okay, how do we see what are our computers doing? All right. And sort of what's the order of magnitude that we can expect? So there's an organization called the Top 500 list. You can see their URL right there, just top500.org, that puts on a competition twice a year that anyone around the world is welcome to participate in. And basically what they're going to do is say, take your computer, it's going to give you a standard test to run. If you're curious, it's called the LINPACK benchmark. We're not going to go into any more detail than that. It involves a lot of matrix multiplication. And it asks you to basically time how long does it take your computer to perform that task. Because they know exactly how many floating point operations it takes and how long did it take your computer to do it. And so then what they do is they'll collect submissions from all around the world, and then they will put together twice a year, once in November and once in June, the list of the top 500 computers on the planet. What are the 500 best supercomputers based on that metric? Who has the highest flop rate? And when I say the term supercomputer, sort of my working definition, if it appears on the top 500 list, it's a supercomputer. Okay? And so the most recent running of this was just back in June. And I've got the results here for you, at least the top 3. And we'll see that the best supercomputer on the planet right now is in China. It's called the Sunway Tiahu Lite. When we were talking about cores momentarily ago, we were thinking about, most commodity computers have 4. Some really good ones might have 8 cores at this point. This computer in China has 10.5 million cores, which is to say it has to get 10.5 million cats to cooperate every time you want to do anything on it. That's a huge feat of engineering to make that happen. And so then what they've got here are 2 different metrics. So notice there's this R max and this R peak. What these are 2 different flop rates. And in principle, it's a pretty straightforward distinction. This R max is the theoretical peak. Based on the hardware specifications that, NRCPC, which is a Chinese firm, put together, what do they think is the best flop rate this computer can attain? That is a theoretical maximum. And it's about 93 teraflops. Okay, so coming back to our metric prefixes, anybody know what teraflop is? What tera, the prefix? 10 to the 12. Okay, so this is now 93,000 times 10 to the 12th flops, which could also be, we could shift that one metric prefix. What's the one past tera? What's 10 to the 15th? Anybody know that one? What was that? Quinta? No. It's peta. So this is basically 93 petaflops. Okay? That's a lot. Now, in practice, sorry, I got this wrong. R max is what they actually observe. R peak, the second one here, is their actual theoretical maximum. So the theoretical maximum is 125 petaflops, and they're actually observing 93. Okay, so that's saying that's 93,000 million floating point operations per second. Is that better than our 60 doing a math minute? Yeah, and that's a huge advance. Okay, so rounding out the list, at least for the top 3, we see number 2 is also another computer in China, the Tianhe 2, which used to be number 1 in previous rounds of the list. With about 3 million cores, and that sort of observed flop rate of just under 34,000, or 34,000 teraflops. And then number 3 on the computer is sort of a newcomer. It's been on the list before, but it actually leapfrogged quite a few spots in June, is this Swiss national computer, the PIS Dint system in Switzerland. Question?
Do you know what these computers kind of like? Do you know what computers like normally do?
Yeah, well, that's a great question. The question was, what do sort of commodity computers do? Hold that thought. We will certainly come back to that in a moment. Okay, so notice, given the country that we're in right now, where is the United States on this list? It's not in the top 3. Does anybody want to take a guess? What's the highest ranked computer in the United States on this list? What was that? It's certainly under 25. Oh, 125. Oh, no. Our top computer is way higher on the list than 125. Higher meaning like better. Number 17. I heard number 47. It's actually kind of sad. This is the first semester. It's number 4. I can only fit 3 on the slide. Sorry, I just only have that much room. Like I said, Switzerland leapfrog. Number 1 and number 2 were both there back in November. Number 3 used to be a computer called Titan, which is housed at Oak Ridge National Laboratory right outside Knoxville, Tennessee, if anybody's been there. If you're curious, just for my moment of bragging rights, I used to work 200 feet from that machine when I worked at Oak Ridge a few years ago. It wasn't called Titan, it was called Jaguar, but it was still a very fantastic machine. Yep.
I can't quote the name right now, but it was like this computer that they put on Jeopardy. I forgot the name.
Watson?
Yeah. Is that there anywhere?
So Watson is a harder computer to evaluate because it wasn't actually designed for doing this type of benchmark. So the question was about, everybody remembers the IBM Watson that appeared on Jeopardy a few years ago that lost horrifically in that last final Jeopardy round? I don't think it lost the overall competition, but it certainly biffed it on the last final Jeopardy question. It was the American city that has 2 airports named after World War II stuff, and it came up with Toronto, which was problematic in the sense that that's not even an American city. Now, the good news in Watson's defense, it had like 18 question marks after it, indicating that it really had no idea that was just a stab in the dark, but it was wrong. Anybody know the correct answer? What's the American city that has 2 major airports named for World War II things? It's not New York.
It's a city or state?
It's a city. Chicago, Midway and O'Hare. O'Hare was a general, Midway was a battle. Anyway, I was living in Chicago at the time. I got the answer right. Okay, so anyway, IBM Watson, I don't think ever placed on this list, but part of that was it was designed for a different purpose. These flop rates here are measured using a very specific benchmark, and we've realized in recent years not all computers and not all tasks work well with that benchmark, and so Watson was designed for a very different thing so that it probably would have performed very poorly on this particular test, even though if maybe we wrote a different test more suited for the type of data analysis that it was trying, it would have been maybe probably very near the top of the list at that time for that particular metric. Okay, but that's a great question.
Like a chess game, maybe?
So IBM Watson actually wasn't designed for chess either. You're thinking now of the Blue Gene and Garry Kasparov back probably before you were born, mostly because I was about yay high when that happened. No, IBM Watson was designed more for doing quick information retrieval, and so the issue is it had a really good connectivity so that it had this big database full of information, which is a very different operation than doing basically matrix multiplies, which is what this particular metric is looking at. And this is something that as a supercomputing community we're becoming aware of, that maybe we should have a broader sense of metrics than just this one narrow one. Back in the 70s and 80s when all of this started up, that really was the main operation, so it's the only one anyone cared about. But that's a good segue, because then speaking of other metrics, what's this last column here? And this is something that people have started to care about more in recent years, and that's power. So we now have these machines. I can tell you from firsthand experience, at least from the Oak Ridge one, the number 4 on the list, that computer would not fit in this lecture hall. Okay? So it's a big machine. Okay, I mean, it's really big, it's really loud, and it generates a huge amount of heat. And so one of the questions that's now become an issue as we start thinking towards sustainability and towards greening everything is, what's the power consumption of these computers? How much power do they actually take to run? And notice these Chinese computers, 15 kilowatts. Okay, I know that's nothing by Back to the Future standards. 1.21 gigawatts. Anyone? Okay, there's a few laughs. But that is a huge amount of power to say, I mean, that's basically just under 2 megawatts of power. How many of you have your megawatt light bulb when you go home? Anybody? That's good, because I don't think they make one, because that would be one bright light bulb. But an interesting thing to notice here is that these Chinese computers actually have quite a bit of power. Notice where the Swiss computer is at number 3. Quite a bit less. I mean, it's still in the megawatt range, but almost an order of magnitude lower. And this has become an issue in certain places when they're thinking about computers, is now sort of balancing the portfolio of saying, how can we get good cost, get good flop rate? We can get a really good, powerful computer, but with manageable energy. And maybe there's a trade-off now in terms of looking at what's the wattage, what's the power per flop. And maybe we try to maximize or minimize that statistic instead. So actually, let's go pull up, because I don't remember the exact number, but the American computer is relatively good when it comes to power, as I recall. So we can go to top500.org. You can see there's lists. There's the June 2017. Okay, so Titan's actually, ooh, they upgraded it. It used to be a smaller number. So you notice the one in Oak Ridge here, about 560,000 cores and so on. And then also number 5 is also at the United States out in California. Okay, and number 6, also in California. Okay, anyway, but you can start to see there's this different power rating, and this is something that people have become more interested in recent years, in addition to just the performance, how much power is it taking? Yep.
So basically for the fourth one, is R max the only thing that's keeping us above below the one consistently? Because everything else is high.
Well, so what they're rating here is, yeah, it's just the Rmax statistic. Yep. Yeah, so notice that the American computer actually has a slightly higher expected or theoretical maximum, but it's not observing it. And that's an engineering issue. One story for why the power is an important thing. If you go back about 10 years, and I promise you'll probably have a homework assignment that asks you to do that, you'll notice that Los Alamos National Laboratory, outside Santa Fe, New Mexico, used to be a top contender. In fact, they had the first computer to break the petaflop barrier back in 2000, either 7 or 8. I don't remember exactly when. And they've basically fallen out of contention. They still get computers ranked on the top 500 list, but nothing even remotely close to the top 10. You want to take a guess why? Has nothing to do with computing, per se. Yep. It has nothing to do with the funding, actually. The Department of Energy was more than happy to continue providing computers to Los Alamos. It required too much power. Most of the other national labs that are on this list, Oak Ridge is in East Tennessee. What else, dating back to the Great Depression, is also in East Tennessee that provides a huge amount of abundant power? The Tennessee Valley Authority. Everybody remembers from their history class all of the New Deal? Anyway, so there's a whole bunch of rivers in East Tennessee. They've all been dammed, and they produce a huge amount of hydroelectricity. And so it's very cheap to get energy in Tennessee, which is then why we can have such a power-consuming machine there. In California, there's a huge power infrastructure between nuclear power plants, and now they're starting to get wind and solar and other things tied in, but they can get power. Santa Fe, is Santa Fe really that big of a city? Not really. The biggest city in New Mexico is Albuquerque, which is approximately 80 miles away from Santa Fe. And then, of course, Los Alamos is another 20 miles past Santa Fe, away from Albuquerque. Albuquerque's got the power to run these things, but the issue is the infrastructure that we have going from Albuquerque up to Los Alamos can't accommodate this level of power. And so I guess funding does sort of come back to it, because they looked and said, well, we're happy to provide the computer, but you can't power it. And so then do we want to spend the money to then redo 100 miles of infrastructure up and down, what is it, I think I-15? Maybe I-25, I don't remember exactly, up and down New Mexico, or do we just give the money to California, Illinois, and Tennessee? And they opted for the latter. But anyway, so these are actually important considerations when looking through what's going on. Anyway, enough about that. Okay, so if we now go and start to look over the years and see what's happening, so they've got sort of 3 things here when we start to look at how are computers going. And so they shortened here, so we have, here's a megaflop, gigaflop, teraflop, petaflop, and then, anybody know what the E stands for 10 to the 18? Exaflop? Okay, if you're looking for an idea on what is an exaflop, it's basically for those of you that like chemistry, it's a mole of flops per week. I've never found another use for mole outside of chemistry, but there it is. And so what we see, sort of in green here, is if you were to add up all of the computers on the top 500 list, this is the flop rate that you would get. And notice that we see a pretty steady increase every time they run the list. It's not increasing by much from one list to the next, but it's going up. The actual number 1 computer is a much blockier curve, where you'll notice that it'll see a couple increases and then it'll stagnate for maybe about 3 years. Anybody want to take a guess why it stagnated here for 3 years? From about, what was it, 2013 to 2015? Someone put out a great computer in 2013, and for 3 years no one was able to beat it. And that computer just kept riding number 1, and then China came out with the Tianhe, although this one's a little bit outdated. And then they're showing at the bottom the actual number 500 on the list, which again shows sort of that same steady increase over time. Something to note, though, is again to see that this is orders of magnitude improvement. You know, there's basically a 20-year span here, and you see the number 1 computer 20 years ago was right around this 100 gigaflop mark. I would be willing to bet you commodity machines are about there. Okay, your watch and something is probably down here, like a smartwatch or an iPad or something is probably down now around 10 gigaflops, which notice would be somewhere probably in the middle of the list 20 years ago. And now we're all the way up here. And so this sort of comes back to your question, what's the peak flop rate of your laptop? So most people here probably have, or you've seen the commodity laptop. You have an Apple, you have a Dell, Lenovo, whatever the case may be. And you just went online and you bought it, and a few days later it showed up either at your dorm or your house or wherever it is. Anyone want to take a guess? What's the flop rate of that machine? We want to take a guess on order of magnitude. I'll throw the last slide on so you can sort of see. Giga, tera, peta. Do you think your laptop is getting a petaflop? No, not even close. The petaflop would still very much be near the top of the list. Well, sort of maybe near the bottom of the list now. But your, $1,000, $1,500 computer is not going to get anywhere near a petaflop. Okay, so maybe gigaflops. Do we want to go maybe 1 gigaflop, 10 gigaflops, or maybe going to be a little bit lower, sort of in the 100 megaflop range? What do you think? Something closer to 1 gigaflop. Okay, anybody else want to put their neck out there? Closer to 100 gigaflops? Okay. So that actually turns out to be right. There's a link here. You can click the here thing if you want to see more info. But most commodity computers right now that you can just buy from Apple, Dell, Lenovo, whatever, are between 50 and 100 gigaflops, depending on how you sort of customize the computer. Which actually sort of brings up an interesting point. If we go back and look at this list, what that's saying is that the computer that you might have bought a few weeks ago or maybe a year ago when you started college is basically as powerful as the best computer on the planet when you were born, assuming most of you are about 20 years old. That's how far computing has come in 20 years, to the point that that was the best on the planet, and it's now something that everyone can just buy for $1,000. I think that's pretty cool. So imagine where we'll be in another 20 years. Okay? So, sort of a question again, like I said, I'd like to talk about some societal issues and historical. Who funds these supercomputers? So we've seen that they have this massive number of cores, they require a huge amount of space, an absorbent amount of power. Who pays for all of this? I think that's an important question to think about. Okay. So the answer, at least within the United States, is up here on the slide, and it's predominantly 4 agencies. The Department of Energy is probably the #1 supporter of supercomputing in the US, along with the National Science Foundation, the Department of Defense, and the National Security Agency. Okay, all of those are components of what? More specifically? The federal government. Uncle Sam. So who's paying for the supercomputers? We all are. Your government thanks you every April. Okay? And so, at least within America, most of our computers are built by, IBM and Cray, 2 computer makers. Intel and any more NVIDIA are usually providing the chips for what powers them, just if you're curious. And so maybe the question from a civics perspective, why do these governmental agencies fund supercomputers? Anybody want to take a guess? I'm guessing in at least a few of those cases it's obvious. Why would the National Security Agency fund a supercomputer? Because they want to what?
So I guess I could pretty much go back to GPS here because they could use that to improve the GPS a little bit.
So to improve the GPS, most of the GPS stuff we could do a run on a commodity computer in no time. We don't need supercomputers to do GPS. Yep?
Because cybersecurity is becoming more.
Yes, cybersecurity. They want to read your emails. Absolutely. We'll talk more about cryptography and the cybersecurity stuff in 2 units. But yes, that's absolutely the primary answers. National security. Okay, and maybe from the National Science Foundation's perspective, innovation. We want to do research. Okay, fine. The rest of them, it's entirely national security. Department of Defense, do they care about national security? Yep. Does the National Security Agency care about national security? I certainly hope so. Okay, so now, maybe the question, and notice I put in here, predominantly the Department of Energy is funding these things. So maybe the question, if national security is the answer, wait a second, the Department of Energy? Why is the Department of, what? Are they really in there with national security? Does this seem sort of surprising or counterintuitive to anyone? It's okay to raise your hand. Really, everyone just believes that what I'm saying is gospel because, my, do I have a great car to sell you. Okay? Okay, does anybody know, so take a step back. What is the main goal of the Department of Energy? Does anybody know? Anybody want to take a guess?
I guess, easier ways to give us energy.
Okay, to find easier ways to give us energy. Yep. To find new sources of reusable or renewable energy. Sure. Anybody else take a guess? Conservation of energy. Those are all really great answers, and they're entirely wrong. So if you go to the to the DOE's history, and there's the link there, you can get this statement on their website. The Department of Energy is one of the most interesting and diverse agencies in the federal government. Activated on October 1st, 1977, the 12th cabinet-level department brought together for the first time within one agency two programmatic traditions that had long coexisted within the federal establishment. One, defense responsibilities that included the design, construction, and testing of nuclear weapons dating from the Manhattan Project effort to build the atomic bomb during World War II, and two, a loosely knit amalgamation of energy-related programs scattered throughout the federal government. Based on that wording, which one is the predominant goal? Number one, it's specific and it's targeted versus a loosely knit amalgamation of energy-related programs. Does that give you any idea what's going on in bucket two? No. So the Department of Energy, their main goal is to stockpile, at least within the United States, to stockpile and protect and steward the nuclear arsenal.
So basically, like, the Department of Energy is pretty much helping out everybody else on that list.
Pretty much. Yeah, so basically, well, they're helping everyone else out, but from the national security perspective, they're responsible for the bombs. Basically, the Department of Energy, and this is just completely my personal take, back in the 1970s, they struggled with what to call it. Because what they really wanted is the Department of we're not giving defense the nukes until everyone says so doesn't fit on the little circle. And so then the question is, well, what do you call it? And they came up with, well, Department of Energy, which, okay, fine. But it has the downside that everyone then thinks the mission is to make renewable energy and to find better energy sources, which is not its primary goal. Certainly in recent years, they've become interested in that, and perhaps less so in really recent years. But that's the goal of the Department of Energy. So the question then, why does this relate to supercomputers? Okay, so now we know the Department of Energy is interested in national security. They're responsible for the nuclear stockpile and making sure the weapons work. Why are they interested in supercomputers? We still haven't really answered that question. Anybody know? Or want to take a guess?
Is it a stretch to say that there's a huge connection between nuclear missiles and computers, and that they're like hackable things?
Okay, so is there a stretch to say that there's a big connection between computers and nuclear weapons to think that they're hackable things? You know, to some extent, that has a funny answer. And okay, so bear in mind, the full answer is classified. I have never held a security clearance, so I probably can't tell you everything. But there have been reports done, I think this was on, it was 60 Minutes or 2020, something like that a few years ago, where they were touring one of the basically decommissioned MISO silos in Montana. I think it was Montana, that had only been decommissioned, you know, just maybe a few months earlier. And they found that all of the machines actually controlling all of the nuclear warheads were basically still 1970s computers that were powered and run using 5¼ inch floppy disks. Can that computer even handle the internet, let alone be connected to it? Not a chance. Okay, so from that perspective, they're not hackable. And to some extent, you might look at that thinking, wait a second, up until a few years ago, some of these computers were run with like 40-year-old computers using 5¼ inch floppy disks. Are they insane? Our computers are so much better today, and our security is being run based on like computers that are our parents' age? On the other hand, you can't hack those computers. They're not on the network. You have to physically be sitting at the terminal, put the disk in, and hit the enter button to get anything to work. And so maybe that's not a bad thing. I don't know. That's certainly be a connection, but that's not why the DOE funds supercomputers. Yep. Because they are what? So is it because computers could potentially use nuclear power to power themselves? I mean, that's already being done. So a lot of these supercomputers in California are probably being predominantly powered by nuclear reactors. And so certainly, you know I have friends that do these types of simulations to run it. How can we better do nuclear reactor design on the supercomputers? But again, no, that's not the main reason. The main reason goes back to history, again. And there's a few links here on something called the Nuclear Test Ban Treaty. Anybody know what that is? Okay, who here saw the most recent Indiana Jones movie that's about 10 years old? The Kingdom of the Crystal Skull? Okay, if your hand isn't up, do not go watch it. It was terrible. But the point being, fairly early on in the movie, there's a scene where Indy's in the middle of a desert, and he comes across this town, and he gets there, he's looking for shelter, and he finds it's completely full of mannequins. And he realizes after about 2 minutes of sitting here that, oh crap, what's about to happen? Anyone who's seen the movie? It's a nuclear test site, and they're about to drop a missile on it, okay, to test the nuclear weapon. So he immediately finds this porcelain bathtub, hides under it, and the nuclear bomb goes off, which, by the way, probably would have been the end of Indiana Jones in reality, but Hollywood's wonderful. But it was a lead-lined refrigerator. The point is, I still think that would have been the end of Indiana Jones in reality. I've only seen the movie once, and it wasn't worth watching again. And that was opening night, sadly enough. Anyway, so the idea is, back in the 50s, we used to conduct these nuclear tests. Most of them were done usually in Nevada. Again, all of that information is classified, so I can't speak to that per se. But we would do these tests to guarantee to, at the time, President Eisenhower, President Kennedy, President Johnson, that if the order was ever given to fire, these weapons were not going to be duds. Okay? And we realized as time went on, by the 1960s, that doing these types of tests was actually environmentally very destructive. And so in, I think it was 1961, 62, it was President Kennedy, I don't remember the exact year, he came up with the first version of the Nuclear Test Ban Treaty, which said no more above-ground tests. And so as far as the public is concerned, and to my knowledge, the United States has not detonated a nuclear weapon above ground since the early 1960s. It's been over 50 years. Various incarnations of this test have gone on, of this test ban treaty have gone on, the most recent one being put in place by President Bush I, back in 1991, which basically said the U.S. cannot conduct nuclear tests. Which is to say, again, as far as the public is concerned, the U.S. has not detonated a nuclear weapon in over 25 years. How then can we guarantee, should the president ever say we need to fire, and should the generals in the military need to do this, how do we guarantee that the bombs are going to work if we're not conducting tests? We can use computers. It turns out there are plenty of non-invasive measurements we can make on the various weapons. Don't ask me what they are, that's classified. But that can give us an idea, is the bomb working? Is it within specified parameters, or is it going to be a dud? And so what we can then do is perform a bunch of calculations and simulations to say, are the measurements that we get from a particular weapon consistent with a weapon that's going to work? And it turns out we need very high resolution on those simulations. We need very good accuracy, and that requires a lot of computing. Thus, the DOE is very interested in supercomputing, and it started funding these things because it could provide these simulations to provide the assurances that the bombs are doing or will do what they are intended to do should that day ever come. Okay? So there's the whole timeline on nuclear testing here, if you're interested, and that's why the DOE funds supercomputers. As it's turned out, over the 30 years, 35 years, that the DOE's really been making this push. Oh, and just as another trivia contest, anybody know what senator back in the mid-'80s was the big push to get the DOE to fund all of these big computers, realizing this task? About 1985, 1986. Anybody ever heard of a guy named Al Gore? It was him. What was it? Anyway. So what we've realized in the 30 years that the DOE's been funding all these things is that these supercomputers have lots of other applications and can be used for lots of things. One of the big successes in supercomputing came about 10 years ago. This was in 2008 with this thing called Operation Burnt Frost. And again, I've got some links here if you want to go see what's going on. And the issue here was, I think, June, might have been July of 2008. One of the satellites that we had recently put up in orbit started malfunctioning. And either the Air Force or more generally the Department of Defense realized that the satellite was going to start falling down to the Earth. But unfortunately, it was in an unpredictable way. We'd lost communication with the satellite. We have no control over its trajectory. And we're not even entirely sure where it was when we lost contact with it. So is it generally a bad thing that this big satellite's going to start falling out of the sky and we don't know where it's going? Yeah, that's probably not a good thing. Let's add to add insult to injury. We had recently just put up this satellite, which means it had fuel tanks that are full or empty. Full. And rocket fuel is usually pretty non-toxic, right? Hydrazine's actually pretty nasty stuff. And so they'd estimated we had probably about 4 to 5 days to get this to blow the satellite down before it hits Earth somewhere. Whether that's New York City or the middle of the ocean, we don't know. And we have a handful of readings to tell us where the satellite was and maybe where it's headed. And so President Bush, the second, instructed Secretary of Defense, Secretary of Energy, so on and so forth, to combine all of these resources from the NSA, the DoD, the Department of Energy, take all of these experts and come together, and they had basically 48 hours to make a prediction on how do we shoot this satellite down. Here's where all of maybe the aircraft carriers and the naval ships are all across the seas that have missiles to do this. Which one do we use? Where do they fire the missile? When do we fire the missile? And can you make this prediction such that you know you're going to hit the satellite, that you're going to obliterate the satellite so that it's not going to come crashing down on some city, and burn up all of the fuel at the same time? Who thinks that sounds easy? I think if you saw the first Star Trek reboot, there was the comment of, this is sort of like trying to shoot a bullet to take out another bullet while you're blindfolded and riding a horse. Something like that. And it turns out it worked. It took about 48 hours. They commandeered all of these big supercomputing resources. The scientists and engineers made a prediction, said fire from this aircraft carrier at this time, in this direction. Satellite gone. Well, what do you mean? They had certain other readings on where the satellite was, but it was not as conclusive of information as they would have liked. Yep. Again, I don't know the details because a lot of that's going to be classified, but this is the story that sort of went through. So if you're curious, this is sort of one of the big heralds of supercomputing and different things that can be done, but it was a really neat story. And then beyond that, what's also been done, this is predominantly NSF, the National Science Foundation, as well as the Department of Energy in a lot of cases, is to actually do open research. And so computing, and in particular supercomputing, is becoming ubiquitous through many different avenues of data analysis. From doing like chemistry and physics simulations. That's long time been something big in computing. Doing fluid dynamics. Who's flown on an airplane? Who thinks airplanes have been ridiculously tested and they're good and all that? That's good, they have been. Has an entire airplane ever been simulated on a supercomputer? No, it hasn't. There's too much detail to get the resolution and all that needed to get the wings, to get the motors and the engines, to get the tail, to get the fuselage, to get all of the components at the level of detail needed to make those guarantees, has historically been more than any of these supercomputers can handle. And so they'll do specific tests looking at how does a wing respond, how does the tail respond, and start to piece things together. And it's probably, the simulation might actually have already happened now, but we're basically right now at that cutoff point where these most powerful supercomputers on the planet can actually simulate an entire airplane, which is sort of a neat thing. More recently, how many of you like to use Twitter or other sorts of social networking? Do you think Facebook has supercomputers? Yeah, they're not on the list. Why would Facebook's computers not be on the list? Well, no, they probably do need that much power because it's proprietary and they don't want to tip their hand on what they've got. But I'm sure some of their computers would be on this list. But there's a huge amount of data coming out. Every time you type something into Facebook, that's a piece of data that they need to store and they want to analyze so that they know what they should recommend to Amazon to sell you next. You think I'm kidding? Okay? And so, but this requires a huge amount of computing, and so even in a lot of these social sciences areas, looking at Twitter and trying to do data analysis requires a huge amount of computing. Just see that from the National Security Administration, where every time an email is sent, and there was the whole kerfuffle, what was it, about a year ago or 2 years ago about renewing the Patriot Act, and what is metadata? Does anybody remember this big debate? Okay, no one pays attention to politics, good for you. But this is a contentious issue, and it's not clear what the solutions are. But what is known is that there's a huge amount of data and a huge amount of processing out there, and supercomputers can be applied just about to any field you can think of in any line of inquiry. If you're curious for more information, there's the Institute for Advanced Computational Science here at Stony Brook. There's also the SCIDAC program, which stands for Scientific Discovery and Advanced Computing through the Department of Energy. And there's a picture of just a whole bunch of results that came off of supercomputers in recent times. So I think we've got a few minutes left, but I think this is a good place to stop. So we will pick up next time going through how do these digital devices work briefly. We'll come back and talk about what are memory, what's RAM, what's a processor. And we'll start going down that way and thinking about how computers actually start to store data. So thank you for your attention. Please post any questions to Blackboard, and have a wonderful day.